thermodynamics state. What I mean, to find the identity of any state of gas, you have to find P in Pascal, T in Kelvin, V in m cube, and N of the gas in mole. So, and you can apply later PV equals to nRT in the case of the ideal gas. Okay, it's important to find these values, of physical values, to find the identity of the state of any gas. Okay, for example, we have the same gas, this one, in the state 1 and the state 2. Here we have P1, V1, T1, and N. We don't, in general, we don't need to change the number of N. We have the same value of N in the initial state and the final state. So in the final state, we have P2, V2, T2, and N. In this case, if we have P constant, we can say P1 equals to P2. And here we have V1 T1N, and here we have V2 T2N. If we have V1 equals to V2, okay, we can say V1 equals to V2, but here we have P1 T1N, and here we have P2 T2 and N, and the same for T. So here it's important to speak about the work done by thermodynamics. What I mean, if I want to change the volume is not constant. What is the quantity of work applied? What is the quantity of energy applied by moving? And in the case of compression, we have to apply a certain quantity of energy consumed to change the volume. I want to calculate this quantity. Let's say, for example, here we have the initial state, and here we have the final state. And inside we have a gas G. Initially, we are here, I push up the piston. In this case, we increase the volume from V initial to V final. Okay, initial volume to final volume. And we have an increasing of volume delta V. You know, here we have this quantity of volume is increased, dV, small dV. I push the piston up with F. How can we push a piston? By increasing, for example, the temperature inside the gas. The gas will push up the piston with F. Okay, I have F applied by the gas. So the work is done by the gas. Okay, I am talking about the work done by the gas. In this case, we are moving in the positive direction. Okay, so in general, the work done equals to the F applied. Let's say F is constant times the displacement. Okay, you know the displacement is dy or dl in general case. So F times dl, you know, P equals to F divided by S divided by A, or F equals to P times A. Is the relation between F and P. If we have a force applied on any object, in this case we have a certain quantity of pressure P. The relation between F and P, F equals to P times A. F is the force applied by the gas. A is the area of the surface, and P is the pressure applied. Okay, in this case, here we apply F on the area A. So P equals to, or F equals to P times A. And you know, this volume here equals to A, the area, times the length, delta L. A times delta L equals to delta V. And here we have P. So what you have to know to calculate the total work done from the initial state to the final state, you can do the integral between 1 and 2 to calculate omega by the gas equal to the integral PdV. What you have to know now, just the general relation of the work done by the gas. I repeat, by the gas. If I say omega, I mean by the gas, because you have by the gas and you have on the gas. If we increase the volume, let's say here, so here we have the general equation of omega equals to the integral PdV, and I say omega by the gas. Okay, as you know, if we have an expansion, if we increase the volume of the gas, if we have an expansion, okay, expansion, we have increasing volume. In this case, by increasing the volume, so the work is applied by the gas, okay? So we can say the energy consumed is provided or released by the gas. It's important to know the notation. When I say the energy is provided or released by the gas, I mean we have expansion. It's important to know the formulation. Expansion, I mean the energy consumed by work is provided by the gas or released by the gas. In this case, the volume will increase. So delta V is positive. You know, delta V equals to the final volume minus initial volume. If we have an expansion, I mean delta V must be positive. If delta V positive and P is positive in any case, so omega by is positive. Okay, so you have to know now, in the case of expansion, we have increasing volume, delta V must be positive, omega B is positive, or omega by the gas is positive. And here you can say, for example, if I give you an example and I tell you, you have energy provided or we have a work provided by the gas. I mean, we have expansion, we have delta V is positive and omega is positive, okay? And the opposite is right. Here, if we have a compression, if I decrease the volume, okay, if I decrease the volume, in this case, we can say the energy is received by the gas, okay, and the work is negative. Why? Because here we have delta V is negative. When we increase the volume, V final is less than V initial, so delta V is negative. So omega by the gas is negative, okay? How can we calculate omega on the gas? We have omega by the gas and omega on the gas. In all the expression here, omega equals to integral PdV, it's omega by the gas. Always omega on the gas equals to minus omega by the gas, okay? So if omega by the gas is positive when we increase the volume, so omega on the gas is negative. If omega by the gas is negative by decreasing the volume, so negative times negative, we get omega on by the gas is positive. Okay, so we have to calculate omega by the gas and we can deduce the value of omega on the gas. In general, we use only omega by the gas. Okay, Now you have to know 2 points, very important. In the case of expansion and in the case of compression, increasing the volume and decreasing the volume. If we increase the volume, delta V is positive and omega is positive. If we decrease the volume, delta V is negative and omega is negative. PV diagram. Here you have to know, in general, we have to take the notation between two states, initial value and the final state. Okay, we go from initial state to the final state. Maybe, for example, here we come from this initial state to this final state by 2 steps. For example, by P constant and V constant. In general, PV diagram, you have to show the values of P in terms of the value of V. P is on the y-axis and V on the x-axis, okay? And you have to put the values of P and V. For example, here, it's an example. I go from the initial state to the final state, okay, by P constant from this point to this point. And after the next step is V constant, okay, from this point to this point. So here we have P constant and here we have V constant because Pi equals to P. Let's say here we have the point A and here we have the point B and here we have the point C. So PA equals to PB, but VA is not equal to VB. And here we have a decreasing of volume, okay? If we decrease the volume, you have to know omega by the gas is negative, okay? Here between B and C, you know we have the same volume. We have the same volume, so V initial equals to V final. In this case, omega equals to O. We don't have any change of volume. Okay, here we can say we have the initial state A to B to C. Okay, the same between A and B, we have the same volume. So omega equals to O. We don't have any change of volume. Between B and C, we decrease the volume. In this case, omega must be negative. And PB equals to PC, and so on. And the last relation between initial state and final state, but as you know here, we go by one process from the initial state to the final state. Anyway, I will talk later for each one. What I want to say here, you know, omega equals to integral of P dV. Here, omega, if you can calculate omega geometrically, omega, the state of the gas at each step can be plotted on a graph called PV diagram, okay? The curve is called the path. If I go from one state to another state, from A to B, we have one path, okay? This line is called path, and this line is called path, okay? The work done by the gas equals to the area under the curve, okay? For example, I go from this state to this state. The work consumed from the initial state to the final state equals to the area under the curve, this one, okay? For example, I go from initial state to the final state. Between A and B, we have this area, but between B and C, you know, we don't have omega. So the total work consumed equals to the area between this point and this point. And also I go from this point to this point by V constant and P constant to calculate the work consumed from initial state to the final state. Simply, you calculate the area under the curve. Simply, as you know, the area here equals to this value times this value. Okay, we can say here delta V times P final minus P initial delta P. If you write delta P times delta V, you can get the value of the work consumed from initial state to the final state. Simply, you can calculate geometrically the value of omega. But in this case, also omega is the area under the line is this one. Here you cannot calculate the value of omega geometrically. So you have to know the relation between P and V. Okay, you can write omega equals to integral P dV, and you have to put the value of P in function of V, and you can calculate the value of the integral. For example, sometimes the relation between P and V, PV equals to nRT. Okay, it's an example. You can put here P equals to nRT divided by V. Okay, you can write here equals to integral nRT divided by V times dV. If we have T constant, N constant, R constant, so you can write here nRT integral dV divided by V equals to ln V. So in order to calculate omega in this case, if you don't know exactly, you don't have a geometrical shape, you cannot calculate omega easily by calculating the area under the line. In this case, you have to find a relation between P and V. You can substitute the value of P by its value in terms of V, and you can calculate omega by using this relation, omega equals to the integral P dV. Okay, just here we will calculate all the value of omega for each state, for P constant, for V constant, T constant, Q constant, or Q equal to 0. But here you have to know, in general, omega is the area under the line. PV is the relation between all the values of P and the values of V, P and V. We start with the first law of thermodynamics. It's a very important relation. If I go from initial state to the final state, okay? Initial state to final state. In general, maybe you have a relation between the changement of the internal energy of the gas between the initial state and the final state, delta E. Delta Q is the quantity of heat added or released by the gas. Delta Q, it can be positive in the case of Q hot. It can be negative in the case of Q cold. The heat added or gained or lost by the gas. Delta omega, you know, omega equals to the integral PdV. So it can be positive or negative if we increase the volume or we decrease the volume. So the relation will be delta E equals to delta Q minus delta omega. Okay? So you know delta omega alone. Okay, here delta equal to the final state minus initial state. delta E change of internal energy, delta Q exchange of heat, d omega a change of work. You know here d omega equals to integral d pdv. Okay, it's omega by. You can say d omega, or you can say directly omega between the initial state to final state. Okay, it's the same notation. Also, you can say dq, delta q, or you can say q between initial state and final state. You can say qif also. Okay, you can say here qif. You can say omega if between initial and final state. Also, you can say EIF. Anyway, we use in all the formulas the work done by the gas. Okay, if you want to calculate omega on the gas, you have to say omega on equals to O minus omega by. Okay. You can write this one dq equals to delta E plus d omega. What I mean, for example, if I give some quantity of heat to the system, for example, delta Q equals to uh, uh, 200 joule, this quantity of heat uh, is divided between the increasing of temperature inside the gas. I mean, we have an increasing of the internal energy of the gas, delta E, plus some quantity of work. If we don't have a change of volume, d omega equals to 0, in this case, this quantity is transferred, is converted directly to the internal energy. Okay? If delta E equals to 0, in this case, delta Q equals to delta omega. The quantity of energy added to the system is converted to the some quantity of work. So here it depends the relation, but in general, you have to know delta E equals to delta Q minus d omega. Okay. Isolated system. So now you know delta E equals to dq minus d omega. In the case of isolated system, so we don't have any, we don't have any exchange between between the system and the outside medium. Okay. For example, we cannot change n. We cannot add q. Q equals to 0. For example, we don't have, when I say energy transfer or transfer, I mean heat, okay, by heat. If the system is isolated, in this case, we have dq equals to O. Also, we don't have any work done on the system, because if we have, for example, we have a piston here. In the case of closed or open system, we have the P ATM, atmosphere, which is equal to 1 ATM equals to 10 power 5 Pascal, applied by the external medium. So this quantity of P is applied on the piston and is on the gas. In the case of isolated system, the system is closed. So we don't have any effect of the external medium on the gas. Okay? In the case of isolated system. Here we have the piston. We have the container are isolated, okay? But you can have the gas is isolated only. So in this case, you have P. But if I take all the system is isolated, so we don't have P ATM. So as we don't have any force applied from the external medium, in this case, we don't have any work done on the system from the external medium. So d omega external equals to O. In this case, Q equals to omega equals to O. We don't have Q, we don't have omega, so delta E equals to O. So E final equal minus E initial equals to O, E final equals to E initial. So you have to know in the case of isolated system, E is constant, okay? Cyclic processes. What I mean by cycle, we have a cycle. First of all, in the case of cycle, I mean you have an exchange of energy with the external medium, okay? For example, we have a quantity of water and I can give a heat to the system. For example, it's closed and here I give Q. So we have Q hot. Or I release a quantity of heat, we have Q cold. So we have an exchange of energy between the medium, between the gas and the external medium. We have Q positive and Q negative. For any cycle, we must have Q cold and Q hot. Okay? So here you have to know we have Q hot and also we must have Q cold. It's impossible. You cannot give quantity of heat and you don't lose a quantity of heat. If you give Q hot, you must have Q cold. Okay? Okay, second point. In the case of cycle, we start by the point and we have to finish by the same point. Okay? For example, if I start by the point 1, I go to 2, 3, 4, 1. I come back to the same point. Okay, this is a cycle. Or, okay, here we have P constant, V constant, P constant, V constant. Here also, for example, we can have A, we have A to B, B to C, C to A. Okay, we come back to the same point. Here it can be T constant between A and B. Between B and C, we have V constant. Between C and A, we have P constant. And the same for the last point. Okay, we start by the point A, by the point 1, to 2, 3, 4, 1. This process is not isolated, simply. Why? Because you have Q hot and Q cold. Anytime you have Q hot and Q cold, the system is not isolated. We have an exchange of heat. In the PV diagram, the cycle process appears as a closed curve. As you know, we have a closed curve. It's not open. The internal energy must be zero. Okay, it's very important point. For example, here we have a cycle. One, we can say delta E of the cycle, of the total cycle equals to delta E 1, 2 plus delta E 2, 3 plus delta E 3 4 plus delta E for 1. You have to do the summation of all the internal of all the exchange of internal energy. Delta E of the cycle, the total one, equals to 0. Okay, for any closed cycle, for any cycle. Also here, delta E of the cycle equals to O, equals to delta E AB plus delta E BC plus delta E CA. And here also delta E of the cycle equals to O. Okay? Energy Q added equals to the work omega done by the system. You know, we have delta E equals to delta Q minus d omega, okay, of the cycle, of the cycle, of the cycle. We can apply this relation for one cycle, and you can apply also for one process between 1 and 2, or for one cycle. As delta E of the cycle equals to O, in this case, delta Q equals to delta omega. Okay, so delta Q of the cycle equals to d omega of the cycle. Okay, you have to know this relation in the case of cycle. The last point, in a cyclic process like this one or any one here, in the case of a closed curve, the network delta omega, or you can say omega of the cycle, equals to the area inside the closed curve. I mean, equal to this one. Okay, this one, the area of this one, equals to omega of the cycle. Okay, and this one is omega of the cycle. This one also. Okay, equals to the area. Okay, if we have only one curve, like before, for example, I take P constant, only one process, in this case, equals the area under the curve. Okay, we have a difference between the closed cycle, between a cycle and between one transformation. I give you here an example. Application of the first law of thermodynamics. You know here we have a gas inside the piston. The gas absorbs 400 joule of heat. What I mean Q hot. When the system gain a quantity of heat, it means Q is positive. When the system lost a quantity of heat, so Q is cold. So Q hot equals to plus 400 joule. And at the same time, does, okay, the gas does 120 joule of work on the piston. Okay, when I say the gas does this quantity of work, so is the energy done by the gas. Okay, the energy done by the gas, look here, when we have Qn applied to the gas, I add this quantity. In this case, the volume will increase, okay? P of the gas increases, and the gas will push the piston up, okay? So as the volume increases, if we have an expansion of volume, in this case, we have omega must be positive, okay? I am talking about omega pi. So equals to 120 joule. If I tell you I have 120 joule and we have a decreasing of volume, so you have to say omega equals to minus 120 joule. Okay, in the case of expansion, you put plus 120. In the case of compression of decrease of volume, you have to put omega equals to minus 120 joule. We have omega, we have Q. What is the change in internal energy of the system? Okay, so as we provide the gas, the work by the gas, if we have an expansion, you can say the work provided or released, okay, by the gas, okay? You can, or by the gas. In this case, omega is positive, okay? Equals to 120 joule. I want to calculate delta E. Delta E equals to dq equal to 400 minus 120 joule. We get finally, I can solve it. So here we have delta E equals to Q minus omega. The final value delta E equals to 220 joule. So as delta E is positive, in this case we have an increasing of the internal energy. We can say we have an increasing of the temperature inside the gas. Okay, simply you can apply directly the first law of thermodynamics. We have a conservation of energy. Q hat added to the system, we have 120 joule consumed as work plus 280 joule consumed as internal energy. So the energy added to the system equal to the energy consumed by the system between, delta E equals to delta Q minus d omega. So dq equals to d omega plus dE. Okay, the summation of the energy consumed by the work and the energy consumed by the internal energy. Okay. Here, in general, I want to study 4 processes. I want to study the case of P constant, in the case of T constant, in the case of T constant, P, V, T, and Q. Okay, if we don't have any heat added to the system. First of all, isochoric process. What I mean? We go from the initial state to the final state with the same volume. V initial equals to V final. Okay. I will talk in details each one, but in general, we don't have a change of volume. If we don't, and omega equals to integral PdV, as delta V equals to O, so omega equals to O. Isobaric process, we have P constant between the initial state and the final state, delta P equals to O. Isothermal process, in this case, we have delta T equals to O. Delta E depends only on delta T. If we don't have a change of T, so we don't have a change of E, okay? In the case of isothermal, in this case, we have T initial equals to T final. So T final minus T initial equals to O, and delta E equals to O. Okay, in this case, E initial equals to E final, and T initial equals to T final. Okay. Adiabatic process, what I mean, delta Q equals to O. We don't add, we don't release any quantity of heat from the system. For each case, I want to study the curve, the path between the initial state and the final state. What is the shape? We can calculate Q for each step. If we increase the volume, if we decrease the volume. For example, if we have P constant, at P constant, we can increase the volume or decrease the volume. If we have V constant, also we can increase P, we can decrease P. At T constant, we can, okay, anytime we can manipulate the system. It depends to the situation, or depending on the situation. Before starting with the processes of thermodynamics, let me define one parameter. You know, we talked about the heat capacity C equals to Q divided by delta T. We talked about the specific heat, small c, equals to capital C divided by M, or delta M, okay? Small c, no, equals to capital C divided by M, or, okay, this one is heat capacity, and this one is specific heat. And we calculated, in general, Q equals to MC delta T, okay? The quantity of heat added or released from the system, the mass of the system, the specific heat of any gas, of any object, times the change of T. Here, I want to talk about the molar specific heat capacity. You have to know the no. Molar specific heat capacity. I mean capital C times P. Okay? At P constant, in general, it's Cp or Cv. Okay? The name is molar specific heat at P constant, or molar specific heat capacity at V constant. So if we have P constant, Cp equals to the molar mass capital M times the heat capacity small c, or not heat capacity, specific heat. And at V constant, the molar specific heat Cv equals to the molar mass capital M times the specific heat small c. Okay? In this case, you know, we can say M times small c, you know, it's here, small c, equals to Q divided by M delta T. Okay? We can say equals to M times small c Q divided by M delta T. and you know m divided by n, the molar mass divided by the mass equals to n mole. So we can say here Cp or Cv equals to Q no, here equals to m divided by capital M, okay? N equals to m divided by capital M, okay? Let me, so if we put here m, capital M equals to n divided by the mass m, okay? So here we have, let me write again the relation here. We can write Cp or Cv equals to m n you know here m equals to m divided by n, okay? So we can write m divided by n times q divided by m delta t. So m with m, finally we get Cp equals to q divided by n delta t, or Cv equals q divided by n delta t, okay? So q equals to n Cp delta t in the case of P constant, isobaric process, and Q equals to N Cv delta T in the case of the isochoric process, okay? So finally, you have to know the relation Q equals to Mc delta T, Mc delta T. C is the specific heat. Capital Q equals to Ncp delta T in terms of N, and Q equals to Ncv delta T. In the case of P constant, we use this one. In the case of V constant, we use this one. Okay? You have to know only these relations. Q equals to Mc delta T equals to Ncp delta T equals to Ncv delta T. Okay. So this is a general case, Cp and Cv, and when Q equals to Ncv delta T and Q equals to Ncp delta T. Let's go now to the isochoric process. Before, you have to know, in any case, but in the case of P constant, V constant, T constant, Q equals to O, I mean in the case of the isobaric, isochoric, isothermal, and adiabatic, in any case, delta E equals to NCV delta T, okay? In all the cases, you can write directly delta E equals to NCV delta T, okay? Okay, we do some application later to understand very well, but you have to know this notation. Delta E equals to NCV delta T in the case of V constant, in the case of P constant, in the case of T constant, or Q equals to O. You can use this notation, okay? And as you see here, delta E is direct proportional to delta T. Any change of delta T, you can get a changement of delta E. Delta T equals to O, so delta E equals to O. Okay,